Welcome to Teddy Talks. In this video, we're going to look at the applications of Newton's third law, and the application we are giving attention here is the apparent loss of weight in a lift. Now, how does this come about? If we say that this is our lift, and there is a person in this lift, there is a person in the lift. Now, when this person is in this lift, his weight mg will act downwards, but in accordance to Newton's third law, there will be a reaction that is equal. Now we are going to look at various scenarios. If there is a weighing machine in this lift and the lift is stationary, what is the apparent loss, or what is the apparent weight of this man? 2, we are also going to look at a scenario. If this lift is moving upwards, what is the weight of the man on that lift? So now, let us begin by, let's say that consider a man of mass m kilograms standing on a weighing machine in a lift. Okay, we know that there is a reaction. There is a reaction R from the floor of the lift. There will be one, a reaction R from the lift, and the weight of the man, acts, or that is the action, acts downwards. Now we are going to look at several cases. Now case 1, let us look at a case when the lift is standing, when the lift is stationary. Now when the lift is stationary, let us sketch. If this is our lift and this is the person in the lift, we are saying that his weight mg will act downwards, and there will be normal reaction in the upward direction. Now if this lift is stationary, it means it is not accelerating, and the acceleration is 0. Now how do we get the net force, or the resultant force? The net force F is should be equal to R. The net force on this person in the lift is 0. Why? Since we know that from Newton's law, F is ma. So now if the net force is 0, this means that the reaction is equal to mg, where m is the mass of the man and g is the weight, is the acceleration due to gravity. Therefore here, the apparent weight of the man is the actual weight of the man. So in this case, when the lift is stationary, the weight of the man is the start reading that we shall have seen from the weighing scale that is stepping on in the lift. Now let us look at a scenario 2. Case 2, when the lift is moving with a uniform acceleration, either downwards or upwards. When the lift is moving with a uniform acceleration, either downwards or upwards. So we're going to see what happens if this lift is moving downwards or upwards. We again sketch our lift. I am taking this to be a sketch of my lift, and this is the person in the lift. Now let us consider the upward motion when the acceleration is upward. Now the weight of the man will always act downwards, but there will be a reaction from the flow of the lift that is equal to that. Now when the lift is moving with a uniform acceleration, let us say uniform velocity, not acceleration. Let's say with uniform velocity. When the lift is either moving upwards or downwards with a uniform velocity, it means the velocity is not changing and our acceleration still becomes 0. Now, if our acceleration is 0, when acceleration here becomes 0, what happens again? In this scenario, we are going to realize that the weight of the man is equal to the reading that we shall be seeing from the weighing scale. Now here we are going to say that for uniform velocity, the acceleration is equal to 0. So the net resultant upward stroke downward force is equal to 0. Since we know that the resultant force F is equal to MA, but we are saying A is equal to what? Is equal to 0. Now, if we consider downward motion, for this lift to move downwards, the weight of the man, mg, minus the reaction from the lift should equal to ma. But since ma is 0, so mg minus r is equal to 0, meaning that the weight of the man is equal to the reaction, and which is the action that can be measured from where? From the weighing scale which we have in the lift. Now let's look at the second scenario. Here is when it is moving upwards. For upward motion, R must be greater than mg to give us the resultant force. Remember, when we are looking at the resultant force, we said the resultant force must be ma. We even went ahead and derived and saw how ma comes from Newton's second law. So this tells me that R minus mg will be equal to 0. Therefore, R here is equal to mg. So still here, we shall say that the apparent weight of the man is equal to the actual weight is equal to the actual is equal to the actual weight. Okay, now this has been scenario number 2 or case number 2 when the lift is moving with the uniform velocity. Now let's look at case number 3. Now when the lift is accelerating upwards. So again, we are going to sketch here, assuming this is the lift, this is the lift, this is the person in the lift. Don't care about my person here. If the lift is moving upwards, the direction of acceleration should also be upwards. And the weight of the man will always act downwards, and the the reaction will act upwards. Now, the resultant force for upward motion, our resultant force here should be equal to the force pulling upwards minus the force pulling it downwards. But we say the resultant force must be equal to MA. Therefore, MA is equal to R minus mg. Now, if we make R the subject, we see that R is equal to MA plus mg. Therefore, R, we see M is common, we pull it out, and we get that. Now, what will happen when the lift is moving upward is this, the apparent weight is greater than the actual weight, is greater than the actual weight of the man. The apparent weight here becomes greater than the actual weight of the man, because we know that actual weight of the man is mg. Now, the moment we get an expression where the weight, the expression is greater than mg, it means that the reading on the weighing scale is greater than the actual weight. So this has been case number 3. This has been case number 3. This one here, not 3, not 2. It has been case number 3. So now let us look at the case when the lift is moving downwards. Let us look at the case when the lift is moving downwards, and we see what happens when the lift is moving downwards. What happens when the lift is moving downwards? So let's look at case number 4. Case number 4, when the lift is moving downwards, or is accelerating. Let's say accelerating. When the lift is accelerating downwards. When the lift is accelerating downwards. Now, if the lift is accelerating downwards, what happens? Let us begin by sketching again. We sketch. This is the lift, and this is the man in the lift. Because we say it is a man, that is a man in the lift. We know that the weight of the man will always act downwards, and then there will be reaction according to the third law that will act upwards, and this time the direction of acceleration is where? Is downwards. Now, like I told you that the resultant force F is equal to the force that is pulling downwards this is mg minus r. But we say the resultant force must be equal to ma. Therefore, ma is equal to mg minus r. So if I make r a subject, I realize that mg minus is equal, r is equal to mg minus ma, and therefore my r here is going to be equal to m into g minus a. Now what conclusion can I draw from this expression? Here it shows, I'm saying that the apparent weight of the man is less than the actual weight. Yes, that's what happens when you are moving downwards in the lift. If you happen to be standing on a weighing machine, your weight will be less than your actual weight, in line with this expression. Now, let us look at a scenario where the acceleration is equal to g. Now, when the acceleration is equal to g, that one is kind of interesting. It is going to bring out a new thing that you might be hearing for the first time. So let us look at we write and say that when a is equal to g, what does it imply? This will imply that r is equal to 0, because a minus g minus a we get 0. That will imply that r is equal to 0. Here now we